Alright, so from the last video, we talked about some general idea and concepts about the simple linear regression, right? So we say we have a random sample of 52 stores, and then for each store, I collected the price of the beer and then how many 12 packs were sold in the store, right? And then based on this sample, we got the simple linear regression equation, which is y hat equals to 2775 minus 248.9x, or more generally, we say y hat equals to b0 plus b1x. But is that our goal for this research? Of course not, right? So we do not only just want to study about these 52 stores, we want to know what is the relationship between these two variables in all stores in the population, right? But we do not have enough time or enough money to collect all the informations in all stores. So what we do, we randomly select a sample, and then we use this sample to estimate the population, right? So we use the simple linear regression equation, which shows the relationship between these two variables in the sample, to estimate the relationship between these two variables in the population. Just like in the previous chapters, we used the sample mean to estimate the population mean, right? We use the sample proportion to estimate the population proportion. And then this is our goal for this video. All right, so now let's go to our note. So this is from the last video. Let's skip it. So we have a sample, and then we want to use the sample to estimate the population. And then from the sample, we got the simple linear regression equation, which is y hat equals to b0 plus b1x. Correspondingly, for the population, we use the population linear regression model to describe the relationship of x and y in the population. Alright, so what's the difference between these two? This regression equation is obtained from the sample. That means whenever I have a different sample, you will have a different equation. But you will only have one population. That means you will only have one equation to describe the relationship between x and y in the population. And we call this is the regression model. Alright, so that means if this regression is about the sample, we call it is equation. If this equation is to describe the population, then we call it is regression model. Alright, so to the population regression model will be mu of y equals to beta 0 plus beta 1 x. Similarly, we use y hat to estimate the population mean of y, mu y. Right? We use the sample intercept to estimate the population intercept. We use the sample slope to estimate the population slope, just like we use the sample mean to estimate the population mean. We use the sample proportion to estimate the population proportion. But remember, for the previous chapters, what we did to get a general idea about the population mean or population proportion, we used the sample mean to estimate the population mean. we did the hypothesis test about the population mean. We get the confidence interval for the population mean, right? So actually what you did is to estimate it, test about it, confidence interval, or just get a range of it. But actually at the end, you never know about what is the exact value of the population mean. You just have an estimation of it. You just know whether it is larger than 30 or less than 30. You just have a range of the population mean, but you don't have the exact value of the population mean. So here will be the same idea. We can make the estimations, we can do the estimations for these population parameters. We can do the hypothesis test about these parameters. We can compute the confidence intervals for the parameters. But we will never know about the detailed value of beta 0. We will never know about the value of beta 1. So for any linear relationship between x and y, the population linear regression model will be just like this. You don't have detailed value for beta 0 and beta 1. Alright, and then let's talk about the second concept. We say from the regression in our example, right, we have y hat equals to 2775 minus 248.9x. And then if we look at this data, for example, we use this store, right? Then the price is 10.06, which is the value of x. And then the corresponding 237 is what? The 237 is the corresponding observed y, right? Okay, now if I plug in the value of x into my regression, do you get exactly 237? Of course not, right? There will be a random error. Just like when we talk about r square, we say another part of variation in y is explained by the random error, right? So even though we have the same value of x for each store, they are not identical, so there will be random error. Alright, so what if I just want to describe one individual observed y value, right? So just like this, right? Okay, so if I want to describe this 237, how I can describe it? First, it will equals to by the regression, right? Remember how we talked about the r square, right? We say it is the proportion of the variation in y that is explained by the x. So this part will be the first part of the variation in y, and then plus another variation in y that is caused by the random error. Right? So the same idea, if you want to explain or describe the observed value of y, you will use the regression b0 plus b1x and then plus a error term. And this error term is so important in our regression, so we have a special name for it. We call this error term to be residual. Alright, so the other way, if we minus these two terms as the both sides, right, there will be E will equals to the observed y minus b0 plus b1x, and then these two terms together is just a y hat, right, which is the predicted y value. And then we will have the formula of the residuals. right? We'll have E will equals to the observed Y minus the predicted Y. All right, so here I just draw a picture of it. We say for the blue point here, right? So um, we totally have 1, 2, 3, 4, 5, 6, for example, right? So I have 6 observations in my sample, and then based on this sample, I have this regression line. All right. Now, based on this point, which is the observed value of x and y, we have this is the corresponding x, this is the corresponding y, which is the observed y. All right, now where is the predict y? So the predict y will be based on the regression, right? So that means you will have the same x value, but now you don't go to the observed y. You will need to use the regression line, and then the corresponding y hat will be the predicted y value. And then you will see the difference between the observed y and the predict y. And then this difference will be just our residual, or sometimes we also call it is just a error. All right, so now I think everything will be ready for the next step, which is we want to do a hypothesis test about this regression. So why we want to do this? For example, if I have a scatter plot like this, is there any relationship between the x and y? Is there any significant linear relationship between x and y? You don't know about it, right? So it shows kind of negative relationship, it kind of shows a positive relationship, or overall it looks like not significant linear relationship, but I'm not sure about it. We want to know whether this regression shows the linear relationship between x and y. If not, you can just stop here, right? You don't need to do the further other test or other analysis about the linear relationship, because they even don't have any linear relationship, right? So what else you did is just a waste of time. So the first thing you need to do is do the hypothesis test about whether there is significant linear relationship between x and y. Alright, so now just focus on since the hypothesis test is just about the population, right? So we just focus on the population linear regression model. Our question is, do we test about beta 0? If we test about beta 0, it doesn't matter whether it is have any specific value of it. It doesn't show any relationship between x and y, right? So beta 1 is the coefficient of x. That means beta 1 kind of show the relationship of x and y. So to test the regression, we want to first, of course, the first step will be the state the hypothesis, right? So we want to test about whether beta 1 equals to 0 or not equals to 0. So think about it. If beta 1 equals to 0, that means beta 1 equals 0, this whole term will change to 0, right? So if this whole term changed to 0, that means it doesn't matter what value x changes, the value of y will not change at all. It will always equals to beta 0, because this term has already turned to 0. 0 times any value will be 0. Right? So if beta 1 is 0, then it means there's no significant linear relationship between x and y. The other way, if beta 1 is not 0, that means this term is exist, right? Okay, if this term exists, that means when x have the value changed, then the y value will also changed, right? That means there will be a significant linear relationship between x and y. All right, so for any hypothesis test, we will follow the 4 steps, right? So we have already done with the first step, state the hypothesis. And then next will be test statistics, calculate the test statistics. All right, so before we calculate the test statistics, we need to check the assumptions. But since the assumptions for testing about the regression is not as easy as what we learned before, it's not like that simple. So we will leave it to the next video to talk about it. And then here we just assume the assumptions are satisfied or good enough to continue with the second step of the for the test statistics. All right, so to test about beta 1, we want to get the t-test statistics. All right, and the t-test statistics will have the formula of b1, which is the estimate, minus the hypothesized value divided by the standard error of the estimate. Will be the same format. But the special thing here is we are testing about 0, right? That means this term, it will be just a 0. So the test statistics, which is a t-test statistics, will just change to the formula of b1 divided by the standard error of b1. So how to get b1? b1 is just from the sample, you get the sample linear regression equation. And then, for example, you have this sample equation, and then this is your b1, right? Okay, so next we will talk about the standard error of b1. So first, you don't need to worry about calculation about the standard error of b1. Right, so let's see from our output, right? So let's analyze price as the x, sale as the y, click OK, and then let's do the regression, fit the line. All right. Okay, so if you look at the output, it will tell you the standard error of b1. So we will talk about this in detail later. All right, so the standard error of b1 will be given in the output. For this case, will be 21.01023. All right, we'll talk about that later. All right, and then here I just want you to understand where does it come from. Although you don't need to calculate it, you need to know that what information it covers, right? What is the standard error of b1? All right, so it will equals to the standard deviation of the residual divided by the standard deviation of x times square root of n minus 1. Alright, so let's talk about each piece. So what is standard error of the residuals? So first, it is called the standard deviation of the residuals. Alright, okay, so or we call the standard deviation of error. It's the same thing. But this SE also have another name. It is called the root mean square error. Right, so it is also called the root mean square error. So now let's look at our output. we will see this row. It shows the root mean square error is equals to 156.6206. That means this value is just a SE, which is the standard deviation of residuals. Alright, okay. Why we have this name? We have the formula of SE, which is equals to the square root of sum of y minus y hat squared divided by n minus 2. Alright, so what is this? We remember y minus y hat is the residual, right? Okay, and then we have the residual squared, right? So we also call the residual as the error, right? So actually this term is the squared error. Right now, I sum of all the possible squared error and then divide by how many of them. Did I just get the average of the squared error? Or we call mean square error, right? So here we have the mean square error, which is short for MSE. We will talk about this MSE later because it is so famous. All right, okay, so now we have the mean squared error under the square root, so the whole SE will be called the root mean square error. All right, so here you don't need to calculate anything about this formula or calculate any formula about this, but here you need to understand the standard error of B1 is obtained from the standard deviation of the residuals, and the standard deviation of the residuals is also called the root mean square error in the output. Alright, so the other part, what is the SX? The SX is the standard deviation of the X values. So where you can get it? You can get it from the summary statistics table. Alright, we'll talk about that once we have the detailed output. Alright, so now we had talked about B1. We talked about the standard error of B1, and then once we have these two, we can get the t-test statistics. So actually, if you have the output, you even don't need to calculate this t-test statistics. You can obtain it from statistics. The next step, find the p-value. Alright, so if you have the output, you can directly get the p-value. Right, so here I just show you what is the p-value, or not this p-value, it will be this, sorry, come back. Okay, so it will be this p-value, so it will be less than 0.0001. That means what? That means the p-value is too small, right? Okay, so the p-value is either from the outputs, or you can also check the p-value from your t-table, just like what we did before. But the only difference is if you check the t-table, you will need the degree of freedom, another degree of freedom, which is n-2. It is not n-1, it is not number of rows minus 1, it is n-2, the sample size minus 2. Alright, so this step is easy. The last step is also easy, I think. Should be easy to you. Right, so once you have the p-value, you can make the conclusion. Right, so we still have the two directions. So we say if the p-value is less than alpha, then what is the conclusion? We reject the null hypothesis. right? That means we have enough evidence to support what? To support our alternative hypothesis, right? So what is our alternative hypothesis? It means there is significant linear relationship between these two variables, right? So we have enough evidence to support that there is significant linear relationship between these two variables, right? So the other way, I just skip it, right? So it would be p-value larger than alpha, then we do not reject the null hypothesis. We do not have enough evidence to support that there is a significant linear relationship between x and y. Alright, so until now, except the assumptions, we are done with the hypothesis testing about the regression. And since we are testing about beta 1, we also get the confidence interval for beta 1. Alright, so for confidence interval for the beta 1, we also have this format, right? The estimate plus minus the margin of error, and then for the margin of error is still be the critical value times the corresponding standard error, right? Okay, then since we want to get the confidence interval for beta 1, then what estimate the beta 1 will be b1, right? Plus minus the margin of error, which is the critical value. So what is the critical value? Since we are using the t-test, the critical value will be t star, right? And then to find the t star, you need to combine the degree of freedom and alpha over 2, and then times the standard error of the estimate, which is standard error of b1, which we found either from the output or just by this formula, right? So you don't need to calculate by this formula. So this is also from the output. All right. Okay, so this is the confidence interval for beta 1. The problem is the calculation is easy, right? So here you still need to look for your t table and then find the t star. But I think you are familiar with that. All right, and the problem is how you interpret this confidence interval. What does that mean? Okay, so for example, I got 95% confidence interval for beta 1 calculated as in our example, let's see, okay, it's 201,225. Alright, so suppose after calculation we got our 95% confidence interval for beta 1 as this. So how you can interpret it? Let's say theoretically we say we are 95% confident that the true or the population slope, which is beta 1, falls in this interval, right? Okay, is this enough for your customer or your manager? No, right? It it is not enough, because nobody will know what does this mean. What does this slope beta 1 mean if they didn't learn about statistics, right? Okay, then you need to interpret into more details about this part. So now, how to interpret this population slope beta 1. So first, how you interpret the sample slope b1. Remember that we say when the explanatory variable x increase by 1 unit, the y will increase by the slope b1, right? Okay, so this is the way how we interpret b1. Now, how we interpret the population slope beta 1. It will be the same idea, right? But now we are all focused on the population. So we say when x increase by 1 unit, the mean value of y will increase by the beta 1 on average, right? So now we change to population slope beta 1, and now we need to combine the confidence interval interpretation and the interpretation of beta 1 together to get the final interpretation of beta 1 about the confidence interval of beta 1. So we say we are 95% confident that when x increase by 1 unit, the mean value of y will increase by 201,225 on average. Got the idea? Alright, so actually we are combining these two interpretations together to get the interpretation of the confidence interval for the beta 1. Alright, so of course if you have a detailed problem or detailed practice, then you need to replace what does x mean, what does y mean, right? What is the unit? So for example, this confidence interval for beta 1 is for the example of the beer's price and number of packs beer sold in the store, that example, right? So we say we are 95% confident that when the sale price increase by $1, the mean value of number of packs of beers sold in the store will increase by these many packs on average. Alright, so until now we kind of get the hypothesis test about the regression, and then we have the confidence interval about the regression, right? About the beta 1. So let's go through this example, and then we will be done with this video. Alright, so this example is still with our old example for the beer sales. Alright, so we want to do the hypothesis test. So we have beta 1 equals to 0, we have beta 1 not equals to 0. Alright, and then for the test statistics, for now we just escape this step because it is more complex than what we did before. Right, so assume the assumptions and conditions are met, then we will use the t-test for the regression slope. Alright, so now we will have the jump output. Right, so we will have this jump output given to you. Your job is to find the useful information from the output for the given questions. Alright, so now for any output of the regression, it will be containing these three tables. The first one is called the summary of fit. So this summary of fit will tell you the general information about this regression. How strong is this regression? Right? How good is the fit? Right. Next table is called the analysis of variance. So actually it will tell you what? It will tell you where does this variance in y come from. Remember that? So one part is from the model, one part is from the error. And then we will have the total observed variation in y. Right, so this table is very important in regression, and it is short for ANOVA. Right, so it will be short for, let's say, ANOVA. Right, so you should already heard about that several times, but I think you don't know what is that. Right, so now you know it is short for ANOVA, which is the analysis of variance table. So this is the second table, and the last table will be the parameter estimates table. So this will tell the information about the sample linear regression equation informations. Alright, okay, now let's look at these three tables in details. Alright, so first, the summary of fit table. The first thing will tell you what is the R square. Remember what is R square? The proportion of observed variation in y that is accounted by the x or by the modeling of x. Right, so this is just a R square. So it will tell you about 73.7% of the variation in y is explained by the x. Alright, okay, and next one is R square adjusted. So for R square adjusted, we will use it in the multiple regression. So let's skip it for now. Right, next, the root mean square error. Still remember what is this? The root mean square error is SE, which is the standard deviation of the residual. Alright, next one, the mean of response. What is response? Response is the y, right? So the mean of the response, which is y bar. Remember, this is not y hat, this is y bar, which is the sample mean of y. So here, until now, we didn't use this information, so I didn't circle it. Right, so next one is the observations. So observations will tell you what? Will tell you the sample size. So for our case, the sample size is 52. Alright, so the summary of fit table tell you the information or the general information about this regression. How good is this regression? Alright, so it will tell you R square, it will tell you the standard deviation of the residual, and you have the sample size. Alright, and next we'll talk about the ANOVA table. So the ANOVA table is very useful, but for now we will keep it until the multiple regression part. Right, so for this part you just need to know that it is the mean squared error. So this is what? This is just a MSE, the mean squared error. But this one is the root mean square error. So what is the relationship between these two numbers? So this is just a square of the standard deviation of the residual. Right? Okay, so this is short for root mean square error. This is just a mean square error. Alright, so next one will be very useful for our hypothesis. It is called the parameter estimates. So look at the name of this table, parameter estimates. What is that? It will be about B0, B1, right? So what estimates the parameters? The parameters will be beta 0, beta 1. So the parameter estimates will be B0, B1. So actually we have two rows. The first row we say it is always called the intercept, which is beta 0. It is not related with the x variable, right? So it is also always called the intercept. That means the estimate here will be B0. It is the standard error of B0. And then this is a t-test statistics for B0, for beta 0. And then the corresponding p-value. But here we do not test about B0. We do not test about beta 0. Instead, we test about beta 1, right? Okay, so beta 1 is related with the x, so the jump or any software will show the name of the x. Alright, and then next one will be the estimate of beta 1. Will be B1, right? Next one, the standard error of B1 will be 21.004942. Next one will be the t-test statistics for testing about beta 1. So you don't need to calculate the t-test statistics. Once you have the output, you have it just in this table. Alright, and then the last thing is the p-value. Right, so you see the probability larger than absolute value of t. That means it is for a two-tailed test, right? So since we have the null hypothesis beta 1 equals 0, the alternative hypothesis beta 1 not equals to 0, right? So it is for two-tailed test. So this is just the p-value for our test. Alright, so now look at our questions. So the first question, what is the standard deviation of residuals? Alright, so first, standard deviation of residuals. What is the notation for it? It is SE, right? Okay, where to find SE? The SE is called the root mean square error. So what is the standard deviation of residuals? It is just a 156.6146. That's it. Alright, so next, what is the estimate for beta 1? First, what estimates beta 1? B1, right? And then you just find the value of B1, which is negative 248.9, right? Okay, so this is B1. Next, what is the standard error of B1? What is the standard error of B1? That's it, right? So this is for the beta 1. You have B1 and then corresponding standard error of B1, right? So it will be standard error of B1 will be just a 21.01. Is that easy? Right? Okay, so now you understand what's going on. Now I gave you the output. You know where to find it and what does that mean, right? Okay, in next question, what are the hypotheses to test if the slope is meaningful? So if you want to test the slope is meaningful, it's the same thing to test about the regression is meaningful, right? So we test about beta 1 equals 0, beta 1 not equals 0. Next, what is the test statistics? Test statistics for testing beta 1, it will be this, right? Remember, it is not about beta 0, it is about beta 1, so it will be negative 11.85. And then, what is the corresponding degree of freedom? Degree of freedom equals to n minus 2, right? So where to find the n? N is the sample size, which is in the summary of fit table, which is 52, right? So the degree of freedom will be 52 minus 2, which is 50. Okay, then at alpha equals to 0.05, what is the conclusion? To make the conclusion, you need the p-value, right? Okay, so here you have the corresponding p-value is less than 0.0001, which is very, very small, right? If it is very, very small, that means we reject the null hypothesis, which means we have enough evidence to support the claim that there is significant linear relationship between these two variables. All right, the last question. Find the 95% confidence interval for the true slope beta 1. So you just follow this formula, right? So you have B1, which is negative B1, which is negative 248.8822, right? Which is 248.9 plus minus the T star. So here, T star, you need to find it from the T table. That means from the T table, you need to combine the degree of freedom and the alpha over 2, right? So we say 95%, that means alpha is 0.05. Divide by 2 will be 0.025, right? So you need to find T of 0.025 and combine with the degree of freedom, which is 50. And then you will find that the T star is 2.009. All right, okay, so 2.009 T star times the standard error of B1, which is 21.01. Right, so you just calculate it, you have this negative confidence interval. Then how you interpret it? We say we are 95% confident that now you need to combine the interpretation of beta 1 with the confidence interval interpretation, right? So we say we are 95% confident that for each $1 increase in the price of beer, the sales will decrease by between 206.69 to 291.11 12-pack cases on average. Alright, so I think we will stop here for this video, and then we will continue for the last part for the assumptions and other confidence intervals and some other problems about the simple linear regression. Alright, so see you in the next video.